Okay, we will begin, I think, in maybe 1 minute. Okay, let's see. Okay, thank you. If you have any question before we begin the class, since last time, please feel free to let me know. Okay, let's begin. So, hi everyone. Today we will cover one special topic on big data security. Okay, so using deep learning. Uh, so, so I hope that you have have gone through the like Python and those library stuff that we covered last time. Yeah, because they are really important, and we will be directly going to some programming projects starting from today. Okay, so so please be prepared. Right, and so this topic is about CAPTCHAS. So if you know CAPTCHAS, that's fine. If you don't know, we will also briefly introduce what it is. Okay, so CAPTCHAS previously the technology was kind of safe to prevent like attacks from people who are from actually bots, right, who are not actually human, and attacks on website. And so what means that CAPTCHAS need people to verify themselves, okay, and by doing some like a test, right? But these days, actually, you know, these tests can be easily broken by deep learning. So that's why, you know, there's a security problem. So it's actually changed how CAPTCHAs have been done these days, okay? Yeah, let's begin. So here's this, here we will show this as an example of the advancement, like the technology advancement of data science that kind of deprecated a security technology, which is a CAPTCHA, okay? And so the technology that makes the security technology no longer effective is because of the breakthrough in deep learning, which we will cover shortly, right? And so again, the security technology capture, we will see it maybe a few slides later. Okay, it's just a test to make sure that you are human, right? You are not a bot, right? Not a kind of like a machine that is trying to break. Okay, because you know if you are writing a small program script, you can do a lot of evil things like way faster, right? You can write a for loop and create a lot of cards. Okay, and so importantly, accompanied with the course today, we will have a programming project, okay, for you to break a capture system using some deep learning models, right? So you will get some experience, okay? And actually, we take this project also with reference to here, this link. So if you have difficulty during the assignment, you can also take some reference there. That's allowed, okay? So we will be using TensorFlow. TensorFlow is a deep learning library, okay? And basically, you will go through how like TensorFlow works. We will cover some of the basics there, right? So, but actually, it's more like a black box because we kind of wrap the whole model there already for you in this project. In the next project, we will open up some models, okay? But here, the model itself, you just need to understand it, and basically, most of the code are already there for you. What you need to do is to utilize the model and you know, break a capture system, okay? Any questions so far? So next I will cover like a deep learning capture, and so then about the project, and then we will have like I will release a project tonight, and then we'll have one to maybe we will allow a little bit more than 1 week for you to finish, right? Okay, so a brief introduction of what is a capture, right? So I think most of you have experienced those kind of things, right? So this, I think maybe with Facebook, okay? The other, I don't know, it's standard, okay? So maybe any website can use. It's like a Google's capture maybe, okay? So this capture, if you look at the acronym, right, CAPTCHA, right? So it's completely automated public Turing test to tell computers and humans apart, okay? So yeah, there's a term called the Turing test, right? So who knows what is Turing test? You feel free to unmute yourself and let me know if you know it's Turing test. Okay.
The Turing test is determine whether someone you're interacting with is truly a human or a computer.
Yeah, exactly. So basically, this is the concept from artificial intelligence, right? So Turing test means, hey, if you just see the output, right, and you don't see who is doing the like a computational response and who, right? So then, if you can tell that that's a computer, right, then the computer, the program didn't pass a Turing test. Okay, if you cannot tell, then basically you pass a Turing test, right? You don't know whether it's done by computer or by human. Right? It's very likely to be a human, but actually it's by, let's say, some deep learning model. Okay, so these days deep learning models in some cases has advanced to like a Turing test level, right? You look at AlphaGo, right? So maybe human is even less effective than computers. Okay, in certain areas. And all these are actually because of the advancement of deep learning, and the deep learning also kind of outdated this kind of capture windows, right? So initially, because this letter is an image, right? You don't really know. Maybe as a human, you can easily recognize this R6, HOD, FQ, right? But you think about it for computer, right? There are other lines, and it's actually a very difficult task initially, right? For maybe 10 years ago. But now, actually, with deep learning models, you can easily get these letters and put here and pass this test, even though it's just a deep learning model, right? So what you can do is you can register, let's say if this is a Facebook, like a registration page, you can register for like you can write a for loop, right? Register numerous accounts, right? So that's not good. Okay. Apparently, there's some solution to avoid that, right? So if your communication are all from the same IP address, right? So apparently, whatever, right? So there's some problems there. Okay. So that's how actually capture these days have been. We'll cover that shortly. Okay. And similarly here, right? So you add some data perturbation to morning overlooks, right? So in this way, maybe for computers, it will be very difficult to recognize, hey, these are the noise in the horizontal curve, right? So we should ignore them and just get the letters. Okay. So this is a challenge response test, which means ask a question, then you should answer. And for human, you should be answered very quickly, very easy. Okay. If we ask you to do a very difficult mathematical question, right, so probably you just don't want to register. Okay. So must be simple enough for human to be able to solve it, right? And these days, actually, there could be even more difficult captures. The reason is these things are really too simple for deep learning models. I think there could be like a bunch of images and say, hey, if you get me all, like take all the images that have a cat in the image or something. So you can see these captures are becoming more and more expensive, more and more difficult, really because the technology demands. Okay. And so it must be simple enough for human to solve it. Even you take 3 images, it's still very fast for human, right? But it should be complex enough for machines not to be able to solve it. Right? Okay, so if, frankly speaking, that capture should also be outdated because it's very easy to recognize whether in these 9 images, which ones have cat, right? And so, yeah, so we will see. Okay, these days, these capture kind of are getting outdated. Okay. So you must be able to produce like new challenges quickly as a, as a capture system, right? For example, if you have new users registering, right? Let's say register to a Gmail or somewhere else, okay? Some other accounts, right? And you should generate different captures, right? You cannot define a finite static captures, right? Using this as an example, let's say, hey, I just have well-designed those kind of images, but I have maybe 5,000 of them, right? So what people can do to hack your system is really, right? So I can hire maybe many people, right? Like using crowdsourcing, and each one can contribute to what they see and what they think should be the answer, okay? And then we save all these potentially 5,000 results into a database. And then when necessary, I do an image matching and then get it to work, okay? So let's say I pay each person $1, and with $5,000, I hack the system, okay? And of course, because it could be random, maybe you need maybe 10,000 or 20,000, but again, it's easy to hack, okay? So what it means that you cannot have a finite set of disturbed images here in this example, right? You should randomly generate right? So you generate random words and then do random interpolations, right? Every two different captures should have totally different images. Okay, they should not be like the same image. Okay, so it should have produce a new challenges. Okay, very quickly and also cheaply, right? If you compute this thing in 1 millisecond, it's fine. Okay, if you compute this in 1 day, that's crazy. Right? So, okay, and then it should be interpretable by people. Okay, there are some captures that are so ugly that people cannot recognize these words. Right? So that's also not good practice. Right? So a lot of people will turn away from the system. Okay. Yeah. Next is so previously we talked about the capture, right? So I hope you have an idea of it, right? So next is deep learning. Okay. So if you look at like this, the recent maybe 5 years, right? So data science term and like deep learning AI has been so hot, right? So, but you think about the AI term, right? So it has been here for maybe half a century, frankly speaking. Okay, why it's like there's also AI winter, right? And why suddenly it becomes hot? It's really because the effectiveness of deep learning. Okay, right? So if you really want to do strong like AI and data science, of course you should understand deep learning well. Okay, and there's a course in I think also this semester taught by Tracy, right, Dr. Tracy Zhang. It's also on deep learning, right? So here we will have some overlap of it, but we will really cover it in very high level and really faster, okay? And because we want you to get a quick idea and be able to work on the project. That of course may cover in more detail every step to help you memorize those modules, okay? So we will briefly give you an idea, okay? Because this is the introductory course to data science. Right? So where is deep learning useful? Okay, deep learning is useful when the input are like difficult to encode or pass, right? So it's like images, right? For visual recognition, right? If you have images, you have videos, which are stream images, right? Frames. It's very difficult to extract feature from them. Okay, you can manually extract, but they are not good enough. Okay, that's the traditional computer vision, right? Now people all move to deep learning. Okay. So it's unlike, let's say, you have a bank account, like bank account database, right? You have the customers and their savings, right? And their, let's say, their age, their, you don't have those columns that are clearly defined, right? It's just a bunch of pixels, right? So this is raw data. Another example is natural language, right? So just think about, so there are two parts, right? One is speech recognition, right? You have the signals. It's totally signals, right? So temporal, audio signal. And you want to input the audio signal and emit the words, like in text, right? So how do you do that? Okay. Another is, for example, it's just a text, right? And you have the text and you want to do some advanced stuff, right? You understand the text and give some feedback, right? So one example is here, give you a term or a sentence in one language, you want the machine to translate into another language, okay? Right, so this is one example of NLP. Okay. So one thing you need to pay attention is that deep learning is really for this kind of raw data, okay? It's not for this kind of structured tables, right? So for structured tables, you can still use scikit-learn. Okay, that's kind of I think deep learning will not provide too much advantage there, right? It's really, so there are two stages. Okay, the first stage is to extract a table like features, right? So like age, salary, savings, etc. Okay, and based on that, you do a scikit-learn model, right? So to predict whether we should like loan the money or not, right? Whether there's risk with the customer. Okay, so this table row. Any questions? I hear somebody may be asking questions. It's fine, yeah. So if this table row, okay, were not there in these applications, right? If your input is a natural language, a bunch of words, or, in pixels, it's not already there. That's why we need to extract features into this kind of row, okay? Those vectors, okay? Numerical vectors from the raw data, okay? So this is why, we need deep learning, right? So, and it will learn these features automatically using some data structure, model architectures that has been proven to work well. For example, there's a convolution that we will cover today, okay, to get things from those kind of images, a bunch of pixels, okay? And if you want to get a speech recognition, right, so what you need is, all you know, natural language, you should use like a time series, right? So like there's a causal convolution, it's again, one-dimensional convolution because a long time, right? Or you can use like a recurrent neural network, like STM, or if you've heard of like get a recurrent unit, okay? And these days there's a new technology called transformer, okay? Transformer, so like a bird, Google's bird, if you've heard of it, okay? So they are kind of ways to extract from sequence, right? A time series of signals, or you know, a sequence of words, okay? But just keep in mind, right? So you know, regular machine learning is go from a row per data becoming a table, right, to the prediction for each row, okay? But deep learning is first you want to use some module to extract features into this kind of row, right? So a vector numeric values for each, for example, for each image, for each sentence, okay? So that's the key difference. All right, so the kill applications can also be combined. It doesn't. Most of them are in like a visual and you know, speech, or you know, in natural language text. Okay, and these are what humans feel intuitive, and they can also be combined. Let's say in your model, you can train. For example, you give the training data. You give a bunch of images. Each image is with some sentence describing the image. Okay. Then once you give enough of them and let the model train, and the model will be able to see a new image, right? And then it will emit a sentence describing the image. For example, here, if you look at, this is a man in black shirt. Yeah, this is a really black shirt, right? And playing guitar, right? So let me see. Okay, so playing guitar, right? So this is kind of accurate if you look at it, right? It can zoom in and see really there's a guitar in the put here, right? And it's like a magic. Okay, so if you are interested, you can look at how this is called image caption. Okay, and it's very useful. Just think about it. In the old days, if you look at like a Google image search, etc. Okay, and you rely on people to give annotations, like tags. For example, if you have a image like this, you should say, "Hey, kids," right, and a toy, right? And some people tell you, and then you can index the images associated with this word. Okay, now you don't need it. Okay, so you just need the image, right? Because we have a trained model, and you give the image to the model and the image some keyword, right? Like yarn and Lego toy, like construction worker, like orange vest. Okay, and then when you search, let's say you search for construction orange vest, it can match this sentence and give you this image. Okay, even if your original image doesn't contain any words, right? So it can, you can use Google image search to find, right? So that's a lot more powerful. So yeah, why deep learning? Right. So there have been so many models proposed earlier, right? And even though, as we said, if you look at those image and sentence, right? So even though we say that there's no obvious way to extract features, there has been decades of research studying specific ways, fixed ways to extract meaningful features from it, right? So why do we need deep learning? Because deep learning learns those features just from, just from the data, okay? And rely on some general models to extract features. And the learned features will be much more effective than human extract features using some rules, okay? So basically these days, everyone is using deep learning, okay? Combined with some like traditional methods, but the backbone is usually a deep learning model. And oftentimes it's a pre-trained deep learning model, let's say by Google, right? So because maybe they spend $1 million over many data sets and train the model, right? You want to use the model and do some fine tuning, okay? And then you don't need 1 million samples to tune your data. You just need 1,000, right? So that's an example how you use it. We will see these things later, okay? So put simply, it works better than others, right? It works better than if you use human extracted the image features and then put a support vector machine there, right? Okay, and the deep learning is just much better because this feature extraction stage is also done automatically from the data. It's called, if you look at some keywords you hear these days again and again, right? So one is called data driven, okay? Okay. So data-driven is just saying, hey, you just give the general model and fill the data and tune the model promise until it can be effective, extract meaningful features from the data. Okay, it's learned just from the data. Previously, maybe we don't have such strong models and hardware to utilize the models. Then we are knowledge-driven. You need to have some experience and encode this knowledge into your data. Okay, and there's another term called end-to-end training. End-to-end. Okay. Let me run this time. And to, okay. What does this mean? Okay. This means that this model, you don't need anything else to do additional stuff. Right? So just in the training data, you inputted this image, outputted this sentence. Okay. And this is end-to-end. Okay. And then if there's some bias that it's not predicting the sentence, the model will tune it until it finally will predict sentence. So what you need to do is really just to provide the input on the one end or Y on the other hand, okay? And then see how, let's say you have a prediction of the sentence, how far away these two sentences are, okay? And then penalize the model a little bit so that it will move towards the right direction. It's a little bit difficult to understand now, but we will see the great descent shortly, then it will be clear, okay? Yeah, it's just words, okay? And so it's better than others. Okay, and there are people say it's alchemy, right? So frankly speaking, the whole discipline of machine learning is kind of optimization problem. So you have a loss function. We'll see that later. Okay, and so basically, let me give an example. Okay, so originally, so what is before deep learning? Right? Before deep learning, something that is hot is something called like graphic models. Okay, one example is LDA. Latent directed allocation for top model. Okay, but for this kind of graphic model, you need to encode your knowledge. Right, so this is called latent directed allocation to learn from text, right, with the topics. Okay, according to words and the text. Okay, and so this model, you see these arrows, right? These prior distribution, etc. Okay, you need to encode these units. Okay, and these address between units, and then learn the primary from that. Okay. Now, what does deep learning say? Okay, deep learning is saying, hey, just give those general models. Okay, which address should be important, which address should almost be zero. Just let the model learn from the data go. Okay, let's say, hey, you give the model the image in the input, the sentence to the output. Okay, and keep doing this. Or if you are doing translation, give English and French on this side, and keep doing this until these green weights are tuned accordingly. So finally tuned to what is reasonable to the model. Okay, so to the data, because the knowledge can be biased, but then you tune from data, it's going to be more accurate. Okay, but of course it's more time consuming to train and need a lot of data because you have so many more models, more parameters here, so many apps, complex models. Okay, so this is basically a high-level idea. Any questions? And why people are saying, hey, this is alchemy? Because, why this kind of structure, right? But this structure is for general data, right? Vector features, okay? There are also like if you have a tensor, right? You have an image, RGB on the channels, and they have pixel values. Then we'll use another structure called a convolution that we will see today, okay? And maybe for others, so for different data, you need a different feature extracting structures. Okay, for example, there's a graph convolution. Okay, so if your input data is graph, right? So you need to use a graph convolution. Okay, if your data is regular convolution images, right? So just to use a convolution now. Okay, and let me see. Yeah, so you need to use this kind of structure, right? Of course, the last layer is always dense layer. We'll see that later. Okay, like those things. Okay, and if your input is, let's say, sentence, right? So then you need something like transformer. Okay, so it's like a Lego toy, right? So no, we should add the. So let's see whether we have. Maybe we can use BERT. Okay, Google's BERT is a transformer-based model. Then it will be clear, right? So what you do is, hey, you give a sentence here, word 1, word 2, word 3. Right? And then it will emit some context-aware vectors. And these vectors are extracted vectors, like in your relational table, where you will finally do a dense layer to do the prediction. Okay? Whether this word is, so this is like a translation, for example, when you, right? You emit English there and emit French out. Okay. So for different input, right, raw input, you need different feature structures. Okay. Yeah. So there's a student asking why deep learning works better than machine learning, because there are more parameters. Okay. And when you have enough data, right, model is not end-fitting, then it will work better. Because human, if you encode the knowledge, it's going to be having bias. Right? So you can capture the main trend, but you will miss some other important trends. Right? So you need to propose some models. And there's a saying that there's no correct models, there's only useful models. Right? Because you always make some assumption that may not be meaningful. But one cautious thing to take care is that no matter for deep learning and machine learning, basically give a general model and do the data-driven training. Okay, so that's kind of way of giving up your control of the model. Okay, if you are doing science, right? So this is more like engineering. If you are doing science, you want a so-called first principle method, right? So like this kind of rules, let's say the Newton's laws, etc. Right? So you really need to understand the internals. Then this is not a good idea. Okay, but this is usually useful. Say you don't care about what's inside, right? So for example, if you look at this image, I don't care. I just want to see where is the light, right? So the light is here, right? But how I know, right, in my brain, how it functions, then I can recognize this light source. You don't care, then you can use a deep learning model. Okay. Right. So this is yeah. This is also called artificial neural network. Right? So this is like a neural network where each unit here is like a neuron. Right? So this is a connection between different neurons. Okay. So this deep learning is just have many layers of this. Okay. If you look at examples here, like this model. Okay. This is just an example. Right? This is actually a lot of layers of this thing. Okay. You can have many layers. Okay. And here you don't need to understand everything for now. This is not a deep learning course, but give you a mindset to understand all this stuff. Right? And when you really look at it, you are looking at it from the right angle. Okay. For here, we will just cover a very small subset of it. Okay. And if you really want to delve deeper into deep learning, there's a paper with, and this field is like crazy. So state of the art. There are different topics. Okay, computer vision. You can do object detection. And you can do denoising, like super resolution. Okay, and you can do sentiment analysis and question answering using natural language. Okay, medical imaging. I could find the brain tumors. Okay, etc. A lot of stuff. But in the play games. Okay, the reinforcement, deep reinforcement. Okay, and yeah, if you are interested, each have a lot of papers and a lot of models that you can study. Okay. Okay, so here's the answer. Right? So why deep learning? Right? So Yann LeCun is one of the founders of deep learning. Okay, there are like three big guys in the field. Okay, and they get the they get the Turing Award. Right? So just for deep learning. Okay, and in a conference called NERPS, now it's called NERPS. Okay, so because this has other meanings, they think it's not nice. Okay, so this conference actually is the top conference in machine learning. Okay, so there's a keynote speaker, invited keynote speaker, Ali, gave a test of time award talk. But test of time award means, let's say, if you have a paper published, let's say after 10 years, this paper citation is highest among all papers in recent 10 years, but then you get the award. Okay? And there, actually, when Ali gives the talk, he basically says, deep learning is very close to alchemy, right? It's a try and hey, this CN works better for images, the other one works better for natural languages, like for transform. But why? Right? So we know the trend is okay, but we don't really know what is happening under the hood. Okay, it's data-driven totally, right? And so I kind of partially agree. Okay, but Yann LeCun is feeling actually exultant, right? So he thinks this is wrong. So they have those kind of Twitter arguments. Okay, But that's not important for us. We just need to know these tools, right? And then we will be able to use these tools. Right? And in application, like we want to break that CAPTCHA right, in this first project. Okay. Any questions before we move on?
Yeah, is there an advantage of having more or less of those layers in the neural network?
Mm-hmm. Oh, so
like when you go, if you go one slide prior to this one, there was like multiple layers in between. What's like the advantage of having multiple versus not so many layers?
I see what you mean. Yeah. So let me see whether we can find an image for that. Okay. So basically, it's a the short answer is that people find more layers helps. Okay. So for example, if you look at a Google Net, Google Net. There are a bunch of layers, very deep layers, right? People find, hey, when I stack, it helps. But in a way that to convince people, we can say that these things are extracting higher and higher level features, okay? Right, so there's actually a way to understand this, but I think these things are still just to make sense of it, try to give some theory, but deep learning these days have no strong theory behind. Okay, so for example, CNN visualization. Okay. Let's see, layers. I think we will find something good. Okay. Yeah, this is a typical example. Okay. They think that let's say the low level in convolution net that we will see later, because convolution net you will see there's a filter which is very local. You just look at the local patch. Okay. So initially, if you just look at a bunch of pixels nearby, you will just detect those edges, right? And this is maybe the first layer's output. Okay. Yeah, there's a student asking, because we have the deep learning course, right? So this is, we will cover some of the models, okay? But this is data science course, not deep learning, right? So if you are interested, you can also consider to take that deep learning course or take some online courses. Or you can ask me, right? I can recommend you some videos, okay? This area is like crazy. So you just look at the timing. If you look at the citation of this guy, he's very young. If you look at, right? So and the citation is like crazy. Okay, so and let's say one paper in CAPTCHAS maybe 5 years ago. Okay, it's cited so many times. You need so many people publish so many papers just in 5 years. Right? So this area is now kind of crazy. Okay, and so you need a lot of guidance to follow. Okay, but the basic modules like CN, transformer, those things you can easily learn from online blogs or doing some reading material. It's very mature because it's so fast. Here is one pictorial way to help you understand why we're not deep, right? The first layer, you may extract some low-level features, but it's not discrete enough, right? And then these lines, right? So in different angles, we're organized into like, eyebrows, or eyes, and ears, etc., a nose, etc. Right? And then based on this, you have another layer extracting more high-level features, like different kind of faces, expressions, right? So facial expressions. Do I answer your question?
Yeah, thank you.
You're welcome. Yeah, and so different layers work on different parts of data. We'll see that. Okay, we'll see that. But basically, we want to extract features that are higher and higher and higher level. Okay, and finally, those higher level features are kind of like meaningful features, like your bank savings, right, and salaries, age. It's like those top level is called semantics. Low level is called the raw data. Right? There's no semantics. It's just pixels. Okay. We want to extract some semantically meaningful features from the raw data to fit your application. Okay. And the modules usually are universal module, which means the same thing will be used, same structure will be used in different ways. Okay. So yeah, and the purpose of deep learning is to learn these modules so that you know where in which data, in which condition you should use which module to convert the input to the output, and then wire them together to make the application work. Okay. Right. So, and why deep learning, this kind of neural network has been there for a long time, right? So just to stack them deeper. why it was not getting much attention till recently. Okay, so this is because previously we don't have large data. You think about it, right? So if you have so many parameters, you need also a lot of data to tune these parameters. Okay, right. And another thing is that now that you have such a large model, right, so the computation is very time consuming. Okay, and previously we don't have very strong hardware. Okay, and so data and hardware are two different things that push the deep learning. Right? On the one hand, there's a very good human annotated data sets these days, right? Like Microsoft Cocoa, and the earliest one is called ImageNet. Okay, ImageNet is a bunch of images annotated with their objects there. Okay, so like what is in the image? Okay, and I think this is by Stanford Lee, and he paid like $10 per hour, or like to hire some students to annotate the images, and they get lots of images. We'll see that in next few slides. Okay, and another thing is that NVIDIA invested in the GPU. Right? So this is actually called the GPU, right? So because if you just look at GPU, it's for maybe playing games, okay, for rendering. Oh yeah, there's a student asking about trimming deep learning models. Yeah, so you do have the trimming, right? So the pruning of some weak links, right? And but that's really for the purpose. Let's say after you train the model on the server, you want to wire it to your cell phone, right? For object detection, etc. Just on your cell phone or to some drones, etc. Right? So or to deploy to a actual production system, okay, server, right? Where you will serve millions of people. For that case, you need to further like clean the model a little bit, because this is the second stage. We are not covering that, because there's a dedicated topic, how to make the model smaller and cleaner. Okay, there are numerous topics we will not cover all of them. Okay, and so yeah, so this is hardware, right? So I think maybe 2 decades ago in NVIDIA, this is not an accurate number, right? NVIDIA decides, hey, we should move away just from GPU for rendering, right? So just because this is a graphical card, right? Whenever you show, you should have a lot of GPU units, right? Processors to show. Each pixel is done by one or a few, computed by a few GPU processors. Okay? You have thousands of processors in this. But then they say, hey, this market is too small, right? Let's also generalize this to general purpose computing, called the general purpose GPGPU, okay? GPGPU, right? General purpose computing GPU, right? So because of this movement, right? So actually the investment is paying back, especially because the deep learning models need a lot of computing, okay? And this actually pushed, we will see later in the history of, a competition on ImageNet, right? So it's really early on pushed by, Jeff Hinton's group, right? They trained a model called AlexNet, which was neural network based, and it's a little deeper, and they try to use 2 GPUs to train. Okay, so really they use 2 GPUs because by that time the GPU memory is very small. Okay, you cannot fit the model data parameters in 1 GPU. Okay? And then they found, hey, this performs way better than earlier models, like using other traditional machine learning methods, like feature extraction plus support like machine, etc. Okay, and then this area like kicks that. Okay, and a lot of people move through. Okay, and where some results you can go for to learn deep learning. So the first is, I think even in our deep learning course, so here this is taught by Dr. Zhang, or previously taught by me, so I'm covering this as well. So this semester, I think. Okay. And so there's a Stanford CS231N. This is the best tutorial to enter this this area. Okay, it's not covering everything, but it's important that you get all kinds of corners of this area. So when people talk about some concepts, you understand these concepts. It's not totally unclear to you, right? So there's the lecture videos also online. Okay, and I think maybe 20 lectures. So it's not 15 lectures, each maybe an hour, a little bit more than an hour. Okay, that's very good tutorials. Okay, and yeah, I think Lee's group is contributing a lot to help others understand. Okay, so this is one result that we can refer to. And there's a book by Ian Goodfellow. So Ian Goodfellow is another big guy in deep learning. If you've heard of like GAN model, right? Generative adversarial network. Okay? But I don't think, and just Benji, I think is one of the Turing Woven. Okay? But I don't feel this book is very readable. Okay, so I would always recommend just to go with this video, right? And do some homework. Or you take this course. So they are basically covering something similar. Right? The course, if you exactly follow the course assignment here, that will be a lot challenging because it's in Stanford. Okay, and that's not enough because they are teaching you low-level things. You implement different modules yourself. Right? And it's not so useful because these days, you need to pick a deep learning software. These are libraries because you don't care about how to program these modules, but you care about how to combine these modules for your application. Right? Then you need to either learn TensorFlow. TensorFlow 2.0 these days are very dominating because a lot of more friendly support with Keras. Right? Another is called PyTorch library. Right? So these two Python libraries are kind of, the mainstream ones. You can choose either. Okay. Previously, PyTorch is more popular because it's easier to program. But since TensorFlow has a 2.0, which is a version 2, okay, right? Google found, hey, it's because they're competing. Right? TensorFlow is by Google, and so PyTorch is by Facebook because they're competing something. Right? Hey, Facebook's tool is more user friendly. That's it. They do a second version. Now I think TensorFlow is a safer, technically 2.0 is safer library to buy in. Okay. Yeah, let's continue. Okay, so as we said, we need the GPUs, right? GPU has been there pushed by NVIDIA. Another important reason is we need the data, okay? And if you look at how the deep learning area really kickstarted, it's really, Fei Li prepared the data, and then, Jeff Hinton's group tries the old models using the data because previously we don't have so many data to try out, right? So then try this complicated model, and then find, hey, it's much better, okay? And then everything is discussed, okay? It's actually, it's not science from my point of view, it's engineering, okay? So it's really, if something is effective, everyone will move it, okay? Just like something, if it's making money, like stocks these days, okay? Everyone will come in, okay? But we still don't understand well why these things are effective. We are just trying, hey, these modules are effective for languages, that is effective for images, okay? But, and so ImageNet is really big now. Okay, so if you've heard of this, previously people are maintaining some called WordNet, okay, WordNet, okay? I think it's actually, there's no space there, so, but actually I think there's a right way is WordNet, okay? This is something that is organized like by the semantic web people, right? A lot of knowledge graph stuff, right? So you have the knowledge base, okay? A lot of concepts, right? Because when you look at a sentence, it's not characters like P or E like here, or it's really the concept person. And once you have this concept, you need to know person and people and men and women. They are closer than indoor, right? So that's so this is an effort to make concept meaningful. Okay, so there are a lot of words, and yeah, so for these words, right, so we have maybe 22K categories of words, right? So this is basically an ontology of concepts, okay? And for each of these categories, actually, Fei Li maybe paid some people to annotate these images with those categories, okay? And so there are lots of 14 million images, right? It's crazy, okay? So you think about how long it takes for you to annotate an image, right? And we will have assignment to annotate the image, right? So the reason is because, the department encourages us to, do a dedicated project because otherwise you can reuse the same project for deep learning and for this part, right? So it's possible that you want to reuse the project in this course for deep learning, right? If Dr. John didn't discover that, but you think about how many people are doing this project in this course. More than one student doing this, and she will find it's better not do that, right? So this is a way to discourage people just to reuse a project for different data science related courses, okay? And here we will annotate some data set, and then we together try some particular deep learning models because we just see, a lot of deep learning problems, right? So in particular, we were let me see, okay. we will zoom into this area, so-called semantic segmentation. Semantic segmentation is on image, computer vision. Okay, don't think it's semantic, it's natural language. Okay, semantic segmentation, image segmentation, where you segment objects into meaningful, semantically meaningful stuff. Right? So maybe this is a chair, a sofa, or something. That's what semantic means. It's just an image segmentation into different pieces. Okay, we'll look at, we'll try it out in a final product. Okay, try some of those models. You can pick whatever models you like, and we will together do some annotation. You will get familiarized how to annotate images, right, using some software, and then we will combine all the annotations of you guys, and then release to all you guys, and then you can build a model over the data. Okay, to get familiarize yourself with the whole deep learning workflow, how to gather data, do the annotation, and how to build the model, and finally how to evaluate the output. Okay, that's later, right? So it's for the final product. So just stay tuned. Okay. Right. So image data is actually doing a lot simpler thing. Right? So image data is just saying, hey, if I have an object, right? So what is the major content of the object? It's usually just one content. Okay. Let's say if you see a cat in the image, but you also see some grass, right, nearby, right? So whether it should be a cat or grass, right? Obviously, if you are human, you will say it's it's a cat image. Right? So for here, you may say it's a steel drum image because the steel drum is so big. But if you want to think from like a human perspective, maybe a kid, right? But T-shirt, it's also thinking there's some T-shirt component, right? But usually people will not pay attention to this corner. There's something chairs, etc. Okay, right? So there's one particular label that is ground truth, and then we try to see whether we can predict, given the image, the model can predict what's the major content of the image. Okay, and because this is a difficult task, right? You can have multiple objects in the image, right? So what they do is they will have one ground truth, but they will allow you to predict five labels. Okay. And as long as one of the labels, let's say we really think the image should be steel drum. If this is in there, then you are correct. Okay. If steel drum is not here, like a giant panel is there, so I cannot find a steel drum, then it's wrong. Okay. So this is much easier because you don't have to guess right. Just at the top, the most confident one. Right? As long as the top 5 confident labels covers this ground truth, then you are correct. So this is kind of cheating. Okay. So pay attention to this. So there's an ImageNet competition called ImageNet Large Scale Video Recognition Challenge. Right? It's a challenge, right? And different groups can submit their model. I think they probably discontinued these days, but early on they have this with a workshop, maybe with CVPR. Okay, so this is what's happening. I think ImageNet has been prepared by maybe before 2010, but yeah. So and then they hold this competition to try to see people whether they can make less mistakes. Okay, and they are not predicting so many categories. They just take out images for 1,000 common object classes. Okay, and then show you, let's say, a cat face, right? So a cat image, right? And you see whether you predict it's a cat within top 5 guesses. Okay, not a dog, right? Okay, as long as you get one right in top 5, then yeah, okay, right? And then early on, people are still using like traditional models. Okay, traditional model. And what is really changing the story is then, this is called AlexNet. Okay, AlexNet, is by, I think it's by Jeff Hinton's group. Okay, there's a student, or maybe postdoc, I'm not clear exactly. Okay, so they actually using neural network end-to-end models, right? And on this data set. And you can see previous improvement, right? Maybe there are early years also, okay? The improvement really low, right? Just 2%, 1%, 3%, etc. Okay. What does this mean? This is called error rate. Right? So how many mistakes you make, right? It's like if you have 100 images, right? You will only guess maybe 28 images wrong. You will make 28 mistakes, right? You can only guess maybe 70% of the image correct, 30% will be wrong. Okay. So this is not good, right? Especially if you think about these days, people try to do self-driving cars, right? So if you have 30% mistake, that's a big deal, okay? And actually, the area has been something like this slowly for a long time, okay? And until the LXNet, right? So LXNet, what happens is it drops, right? So that's a big deal because every year you just improve for 1%. And suddenly you drop for maybe 10%. That's a big deal, okay? And since then, people see the potential and the more and more models are proposed. And it's all drop, all the way drop, all the way to here, okay? Right. So ResNet is the paper I mentioned in 2016 competition in CVPR, but and they actually do the competition in 2015 already. Okay, the model should be done at least by 2015, and that model is one of the milestones. Okay, kind of last one. It reduces from 28 all the way to 3.6. You can see the previous year is 6.7. So the reason it's a milestone is because previous models are using old models, just because we have the hardware, we have the data, okay? This reduction of half an error is actually by a new structure called the ResNet, okay, residual link, okay? I don't think we need to cover that, but just be aware of this, okay? And this is a new proposal about this stuff. Right. And then there's not much improvement because you already 3%. If you improve at most 3%. So but there's still some slow improvement. Okay. And the important thing to note is that hello. I think let me mute, or if you have a question, you can mute yourself. Otherwise, please keep muted. Thank you. Because we have 80 students now, and it would be crazy if everyone speaks 1 second. Every 18 minutes. Yeah, every minute we have something to speak, someone speak. Yeah. So you can see here, this human will make 5% mistakes. I don't think this makes sense. Right? For human, I mean, you show me 20 images, I should not just always make one mistake, right? So because it's pretty clear to human, right? My guess is because there's ambiguity, maybe two different objects, and someone thinks ground truth is, but now you show another human, he thinks it's this, right? But anyway, so they claim that since 2014 later, all the models predict things better than human. Okay, so this is what's happening here. Okay, any questions?
Is the drop due to just having more data for the models, or like better?
Okay, so yeah, the drop is because if you look at the ResNet, yes. The drop is really because of a new architecture. Right? So this is the previously people just do layer by layer. Okay, previously people just have this. Okay, the improvement is really they find a new architecture that works even better by direct users. Okay, but this the reason all these things. This is residual. Right? So because you have X directly wired to here, you just compute the delta X. Okay, through these layers. Originally, you are computing X.
Didn't everybody had to use the same data for this problem for like the 5 to 7 years until it was like considered solved, right?
Yes, yeah, it's a competition. Everyone use the same data and see who has the best performance. Okay, it's a challenge. Right? So every year, actually, there are many teams competing, and those shown is the best one each year. Is okay? You answer your question?
Yeah, thank you.
Are you welcome? Okay. Yeah, so there's some new modules designed. Right? So they find this kind of the green link here actually helps. Okay, that's a breakthrough, and it really works because it drops the error by half. Okay, even though there has been so much improvement. Okay, it's a half. All right, so and yeah, so here is a story. Right? So just tell you that this model, AlexNet, that really moves deep learning into this challenge and gets attention. It's nothing more than a model that's last century. The reason is we have now much stronger hardware, and we have larger data set. Previously we don't have so many larger data set. Okay, and another thing is that even by that time, so they have to use 2 GPUs. Okay, it's one GPU, this is another GPU. Right, so you can merge them. Okay, just to give you a so these are the milestone systems. This is called AlexNet. Right? So there's also a another thing called CAPTCHAS. Okay, they're the same thing basically. Okay. CAPTCHAS is just to say, hey, this is AlexNet. By that time, you don't have such large memory in GPUs, right? Now, at CAPTCHAS, I can now merge them into one. So this is CAPTCHAS. Okay, and it's just a, these days you will never use AlexNet, right? Because CAPTCHAS is apparently, but it's, you can fit things in one GPU while bother splitting. Okay, there's also limitations there. For example, if you split them, then some of the links are missing. Okay, so for example, those links to here, those links to here are cross GPUs. Okay, it's very slow. And you have to miss some of the links. They are not sharing information enough other than within the GPU. So for example, let me give you an example. So you can see only the last layers they start to cross information. But in previous layers, they are not. Like here, we don't cross information. But if you use one GPU, all these information are passed, right, between all neurons. Okay. Again, here you just relax. Okay, these things are not what we will test you. I just give you an idea, a rough method of learning deep learning. Okay. So later, if you want to go in this direction, you understand what to look for and what's good, what's not good. So what's the right direction? Okay, where to search for things. Okay, so yeah, here we will just look at a particular module called the convolution neural networks. Right? And importantly, we will look at the convolution layer. Okay, this layer really applies to a tensor. Okay, and the tensor can be just an image. Right? So you have an image with height, and then you have channels. Because these color images using RGB scale. Right? So you have red, blue, and gray. Right? So actually, you can have a red map, green map, and blue map, and you stack them together and they become a color image. Okay, so this you can regard as a tensor. And so then you will apply some convolutions, and we'll look at the ReLU why we need these things. Okay, ReLU. Right? So and then we need some pooling. Right? So these days we do away with pooling actually. Okay, but that's the AlexNet old model stuff. Okay, and finally we need a traditional model because you think about it, after this we have the semantic high level, features, like there's a light here, and there's this is the wheel, and this what's the size of this. All these are encoded in maybe the high level features. So again, this is just by imagination. So maybe they are not meaningful to you, but it's kind of helping you understand stuff. Okay, and then once you have those high level features, you just need a traditional machine learning model to do it. Here, the last layer is always dense layer. So the neural net, the traditional neural network. Okay, we also got a MLP. So the last layer is always a bunch of this. Okay, so each layer is this is multi-level. What is this? Let's do deep learning. So this is called a multi-level perceptron. Okay, multi-level perceptron, because what is a perceptron? A perceptron is, hey, you have one output and you connect to the previous layer of input. This is one perceptron. Okay, and you have a bunch of perceptron each layer, and you have multiple layers. So this is called a multi-layer perceptron. Yeah. The last layer always a multi-layer perceptron, which is a traditional machine learning model. You can also replace it with support vector machine if you want, but deep learning really you want a backpropagation, so most people know that. Okay, so yeah, maybe we can take a 10-minute break. We will come back maybe in after 6:10. Okay, we probably will begin 6:12, etc. Okay, and in the meanwhile, if you have any questions, feel free to ask me. Right? Yeah, let's take a 10-minute break. I will be back in 6:10 and wait for 1 or 2 minutes. And okay. And from now on, we will move a little bit faster because these are different modules. Right? And hopefully we can finish this today. If we cannot finish this slide, then we will we will make it a 2-week project. So we will cover this again next week. But hopefully we can just finish it today. Okay. But, okay, yeah. So see you in 10 minutes. Okay, let's begin. Right. So previously, as I said, so you can get relaxed because that's before this slide. Okay, things are not so relevant. But starting from this slide, okay, everything is relevant to the project. Okay, so let's now be more serious and pay more attention here. Okay, so as we said, we are our task is also like images, right? So because we are doing image capture. Okay. And how it works, as we said, using convolutions, you can extract the features of higher and higher levels. Okay, but you want to add some non-linearity. We will explain why. Okay, and after that, you have a so-called pooling. So what does this mean? We want to drop out something, right? So we want to extract the higher level features here. Okay, more high level features. Okay, and then those smaller number but more features, more higher level features. Okay, and then using this, we can do multiple segments. Okay, and finally we have a really high level features, and then we do a fully connected. Okay, so one thing that people are doing this pooling is really from the the high level kind of concept. Another reason is really because the architecture. Another reason is actually because of a simpler reason. Okay, so here you can see finally what you want is a flattened layer, which means each one is just one value, right? But initially your image is just a tensor with RGB channels and the pixels. Okay, this is the face, right? Channels are independent, different light signals. Okay? And you want to extract similar tensors layer by layer, where the face is shrinking. Finally, it's kind of, you can think a stream layer is shrink to one value. Okay, so these features have spatial correlations. Okay, so these are the same like a stroke, right? So, and these channels are independent. Finally, you have a bunch of independent channels, right? Like salary, age, etc. If you look at like a customer of the bank, right? So we want to enlarge this channel dimension and make this face smaller and smaller. Okay. The benefit of this is actually you can see the computation workload across different layers are similar by through. Okay. Because if you still work on such large face, right, then it's computationally more expensive. Okay, if you do pooling and make the face smaller, then here the computation was smaller, right, and the up in the later stages, computation will be smaller, so you can afford more channels. Okay, so initially the channel is very small, and gradually your channels, the independent features grow. Okay, and those spatial localities stuff shrinks. Okay? So this is the idea, and the computation also balances. Because you have the same GPU, right? In different stages, you're still running the same piece of thing. Okay, you don't want something to be dominated, occupy most of the GPU memory and the computation time. Any questions? We will look at the details here. Okay, so basically keep in mind this is a conv-relu, and then pool, and we have multiple segments of this, and finally we have a one layer perceptron. So this is multiple perceptrons between one layer, fully connected. Okay, you can see multiple names. One is called FC, which means fully connected layer, because basically this layer is fully connected. Okay. Another name is called dense layer, because this layer is dense. Okay, the last layer is dense. So that's basically the meaning. I think it's actually this layer. The last, you will have you can have multiple dense layers. Okay, it's then multi-level perception, like here. Okay, so this is just to get you familiarized with how this kind of convolution neural network architecture looks like. And this is really the Alexand, which is the architecture like in 2012. But for simple data, like what we will see, this is good enough. Okay, for very complicated real life data, like 1,000 objects, maybe you want a ResNet. Okay, what we will do is we will work. So for example, we have a data set, right? So called CIFAR 10. Okay, I think CIFAR is a research institute. Okay, 10 means there are 10 classes. Okay, in this data set, and these are the classes, right? So you can see these are all the different airplanes. These are different kind of birds. Okay, right? And so you know the meaning. Okay, each image has a unique label, and you want the machine learning model, right, the deep learning model, see the image as pixels as the input and output the right label. Okay, and there are, let's say, 50,000 training images and 10,000 test images. Okay, then let's see what will happen. Right, so now you can do something like this. So the first thing we want to talk about is fully connect layer, FC, right, so the dense layer. Okay, what that means is that, so firstly, let's think about a naive approach, right? So we only have dense layers, right? So this is what we see previously, right? So we have a bunch of models, right? So without other layers, a bunch of dense layers stacked together. Okay, so that's kind of a very brute force method because we have so many parameters. Okay, all other models are trying to reduce the number of parameters. Okay? So this module, dense layer, fully connected layer, net, is the most brute force method. Let's say we just stack those kind of dense layers together, right? So each dense layer can be regarded as a function f, okay? Where you have the input x and your weight parameter is w, right? So in general, you can always look at the machine learning in this way. You want to predict something called y from the model, right? And where you input it as, okay? So but importantly, let me see why the text is so small. Some way we can make the text larger. So can you guys see this text? I think there should be some way to make it larger. Yeah, yeah. Mm-hmm. Okay, I see. At least a student can see it. So then let's. So y equal to f. Actually, we have some parameter down there. Okay, f theta. Let me use the right pattern. Okay, so that could be. Then we can make it a lot larger. Okay, let's see. So machine learning in general is always something like y, right? So for supervised, okay, there are only two kinds actually. Y equal to f theta x, okay? X is the input, the output of the function is y. Theta is called parameter. This is what you train, okay? This is what you train, so that whenever you give x and give y, actually it's your prediction is y hat, right? And the true label to y, they will be very close. Okay? How do you find the w so that the prediction will be very close to functions? Okay, keep this formula in mind. Right. So again, so maybe I can go beyond what we are talking about here a little bit to see generally how you interpret different concepts. Can you hear me? I see some students cannot hear me, so just want to make sure. Right. Okay. Yeah. So, okay, I see a lot of students confirmed. So let's continue, and we will share the video. Okay, later. Okay. So let me give you an example what this means. Okay. So for example, we talked about support of machine, right? So this is really a let's say support vector regressor. Okay, so for second level. Classification regression, I think you guys need to understand the concept. I think last time we covered it, right, in the first class. Okay, classification for labels, regression is for the others. Okay, so here you can take a look. Okay, so here when you import the support vector machine from scikit-learn, and you will get this model. Okay, right, so let me see where it is. Okay, it's here. So you get this model. I think there's a pipeline, so this is a lot more complicated. Let me see whether we have a simpler example. Yeah, it's always with plotting. So let's find an example that is more easier to illustrate. Okay. So there's always using a pipeline. Let me see. Can we find an example without pipeline? Oh, I think you cannot see it right here, right? So let me put it here. Let me create a new tab. Yeah, example. Let's look at this. So there's some background, but to us, you really don't need to understand how this model works. Okay, so internally, you just need to look at how to write this model. Okay, so here's how it works. Okay, firstly, you include this library, right, in the very basic form. Okay? And then you say, hey, I want to create a model. What is this? This model itself is now if theta. Okay, it's if theta. Okay, let me put the difference. So this model here, now this is f theta. Okay, right. And here theta you actually is internally contained. Right. When you say, hey, we fit, but we put x train here. Okay, but we also need to train it with ground truth y train. Right. So you put here. Right. You give a bunch of training. Okay, and then this will learn the theta. This is what the fit function do. Okay, and after that, if you go to after the model is trained, right, so now what you already have the theta, okay? Okay, now this is f theta with theta already trained from the training data. Now what you do is you give a new x, what you never see, okay, you do the prediction and you will get a y prediction, okay? And this is your prediction data, right? If you know the ground truth, you can evaluate the model, how close it is, right? And then you have the error function and you know how much error, okay? So then you can see the errors and see how the prediction and the actual ground truth in the test data set. Okay, so put simply, everything is theta. So theta also has two parts, right? So first part is called hyperparameter. Okay, so hyperparameter is like you call, let me see. When you call this, right? So you need some human-defined parameters, which you are not for you to, okay, for you to try out, okay, not for the fit function to find the parameter. So these parameters are human-defined parameters, okay, and these are called hyperparameters. Okay, so this is not the fit function we're looking for, okay. Right. So this is a hyperparameter, but fit internally they also have some parameters. Okay. So this is what the fit function is using optimization to learn things. Right. So you can see these are the attributes. Internally they are learning those things. Okay. A lot of those things are actually internal parameters using them. Using your X train, Y train. Okay. So this is the example where you can do machine learning. Another example, if we look at deep learning. Right. So let's look at a Keras example. Okay. Again, this course is not teaching you what each module is, right? But we are teaching you something like, how to interpret input, output, and once you understand the model is doing what, then how to make it work. Right? So this is a CAD, and let me see. I think a lot of things are not important. Okay, it's right here. Okay. So now that we have deep learning models, so basically, let me see whether I can. Now we have deep learning models. What we do is this, right? So first layer, you have X into there, and then you will get some first layer of output, Y1, okay? And then you can put Y1 here, okay? And you get some output Y2, okay? And then you put Y2 here. Of course, this is different, right? This is the first layer, this is the second layer, this is the third layer. They have different parameters, okay? Yes. And you can stack them, okay? Right, so these are the same, okay? This is a particular F. This is F1, for example, convolution, right? And these are the hyperparameters, okay? This X is a tensor input, okay? And then you get an output. This is a Y1, basically. This Y1 can go to the next layer, right? And there's not much hyperparameter, but each thing internally maintains some tensors, which are the parameters, theta, okay? Each one has theta, internal parameter, okay? And so basically, you are stacking them, and again, and finally, you get a model done. Okay, so basically this is the idea. Any questions?
Why are they all using the same variable? Aren't they supposed to be different?
Oh, so this is reuse, right? Because this thing in there and then output. It's just like a programming language. If you can reuse this library, but this is already passing through this F1, right? So this is after passing through F1. So basically, if you look at parameters, it's just a programming stuff, right? So because you don't need the previous one, okay? So this input and the output can be reused here, and this thing after transforming can be used here. Okay, it's the same idea, right? So because we don't need multiple names, they are not used elsewhere, right? If we say y1, y1 comes here, and y2, right? So y1 is not used elsewhere. Okay, so this is just that. Okay, because we don't need the y1, y2.
Is that kind of chaining, putting it on the end, or is that what's the syntax for that?
So this is just the input. So we are talking about
putting the x on the end.
Yeah, we're talking about y f theta x equal to 1. Right? So just look at this is a deep learning model. We have a layer. Right? So each layer, this x is this x. Okay, and you may have some argument here, which is this theta. Right? And this is one portion of the theta. The another portion of theta is trained by the model. Okay, right? And then these are y's. Y's each layer you have an output, which goes to the next layer as an input. Okay, that's how you interpret this. Is this clear?
Yeah, it's like multiplying the weights times the matrix, right? So the x is the matrix, and then the activation function.
Yeah, if you're looking at the
which is in this
for the others, it's not. Okay, it's different layers. As we said, this is all different layers. Okay, just to give you some high-level ideas. Then let's go back. This is a particular layer called a fully connected layer. It's okay. Right. So this is like a particular kind of layer, like the dense layer here. Okay, this operation, this f function is this. Is okay. Right. But later we will also describe some other things like convolution, like activation really. Okay. Right. We will talk about these things. Okay. Right. So now let's take a look at the dense layer. What does this mean? Right. So this is the function, and you have x, and this is the parameter for them, which is what we learned. Right? This is the weight parameters. Right? When you train, you are really training for each layer. You're trying to find the parameter. Okay. And here input is what? So we are just using our model only contains fully connected layers. Then this whole network is called fully connected net. Right? Network that contains multiple layers. Okay. And our input is an image. Our output are 10 numbers. Each number is a score. And remember, we have these 10 classes, right? The highest score will be the prediction. Okay, that's what we are doing. Right. And here in this example, for dense layers, it's equivalent to, if you have an x and the parameter is just a time a matrix to this column, giving you an output column vector, that is y. Okay. Let me see. So here's the scale, right? The scale of it. So firstly, the input is, this is a square matrix. This is a matrix times a column. I'll give you a y column. Okay. So the input, right, is a vector. Okay. But here our input is a tensor, right? RGB 3 channels. Okay. So we need to first flatten it. Okay. Flatten it, vectorize it into, just a row, this is first, the next row will be here, the next row will be here, and this for R, right? For GB, we also set. Then it becomes a vector. Okay. Again, no one do this for images. This is for illustration to tell you what is fully connected layer. Okay. Usually, if you see image as equal to just do convolution, but this is just for illustration. This is actually still going to work. Right? So you see the pixels, we are still using dense layer, right? Which is the convolution layer we just called it. But this is illustration. Right? In order to make it work as an input, we have to flatten it into a vector, and then you time a matrix, and you get a new vector. Right? And this new output should have 10 scores. Right? So cat has one score, dog has one score, we should have 10 scores. Right? If that's the case, what should be the scale? Okay, what should be scale? we know that after flatten these 3 dimensions, we get so many pixels as a column. Okay, this column. And using matrix multiplication, finally we want to have a column of 10 classes, right? And so this scale should be 10 times 3000. Okay. Any questions? All right, I hope this is clear. So, but this is a kind of difficult to understand, right? Just match the scale. So how can we, again, you can add some bias. Right? So for example, you know that most of the pictures are cats, not dogs, but you can have a bias. Let's say if you have, you can add another initial prior column actor, okay? So what I mean is that you can have and plus a column, right? This is a matrix times a column plus a column of 10 by 1. Right? So this maybe cat you have a high score, dog you have a low score, because you are pretty sure most of the image are cat. So you can have a bias.
I think one thing that I remember, but I may not have heard yet, maybe you said it, is that you start off with a matrix of like random weights, and then it gets better every time and those are adjusted. But it starts off with like a full matrix of weights.
Yeah, exactly. But we are not talking about it yet. We are talking about the weight, right? So the fit function, for example, or the trend function, the training weights, and you need to start from some random value. We will cover that later, okay? But you are right, okay? But actually,
so I think my internet's cutting. I'm missing you.
Yeah. So basically, if you look at the dense layer coverage, okay, API. There's an initializer. Okay, this kernel initializer is using by default. If you don't say random normal, it's using a Glorot Xavier initialization. Okay, so basically there's some discovery that if you stack deep, the random normal initialization, like what you just mentioned, is actually has some problem. Okay, like a vanishing gradient. Okay, so there's some default one that people actually publish papers for that. Okay, so initialization. So, and there's papers. Okay, so, and how do this? So by default, actually, you don't care about the initialization. Okay, these libraries handle this. By default, it will use this to initialize. Okay, so that's why we're not covering. Right? So if you cover that, actually, there's a lot of other stuff. And the random normal is, if you are shallow, you can use that. Okay. But anyway, so this thing is what we model is training. Right? So this initial value doesn't matter. I found it will change to do that. And so here's a way to help you understand stuff. Right? So, now we have the matrix. I assume we have 3 classes, cat, dog, and ship. Okay. Right? So now we have this W matrix times a input. The input is a flattened columns. Right? So pixels. Right? We are flattening these 4 columns, 4 pixels into a vector of 4 elements. Okay. And then we times the W, and we will get the 3 classical. But this is what we do. We will also add a bias term. Okay, but then let's take a look at how we get the cat score. So cat score is really, the first row times the first column plus a bias, or the first bias. Okay, so you can see this color, is the yellow color, right? It's all for cat. Okay, and this is for dog score, right? So this is for ship. So it's like each row of the matrix. Okay, it's like a template, right? So this is for template cat, this is for template cat, and this is inner product between the cat template and your input. Because this is, again, just to try to help you understand, make more sense of this. So, all right, so after each dense layer or convolution layer, etc., right, we usually will add a so-called activation function, right? So I think we will let's see why. Okay, so here's the reason. Okay, let's say you stack different layers, right? The first layer is, let's say, W1x, okay? The next layer is W2. So for example, you have, let me do this. For example, the first layer, you have X, right, and the times W1, and you equal to Y1, okay? And then Y1 and times another W2, another density to Y2, okay? So what is the result? This is Y3, Y2 is equal to W2, Y1, right? W2 times Y1. Y1 is W1 X. Okay. What does this mean? This actually, you can multiply these two matrices together. This is another dense layer, right? So if we just do naively stacking the fully connected layers without a non-linearity, because this is linear transformations. Okay, matrix times the column we call it linear transformation. Right? So it's always a linear transformation. So you don't have much descriptibility, right? So the expressiveness is very low. It's like you add multiple layers. It's not much different from just add one layer. Okay, so that's why we want to add some additional function in between. This is called the activation function. That will add some non-linearity. This makes the model actually be able to train well. Okay, and they call it activation because the name is motivated also by neural networks. Right? So you have a neuron. And then you decide, hey, if the signal, electronic signal is high enough, you have some signal pass to the next neuron that you are tracking, okay, the next layer. Otherwise, you don't find electronic signals. So this is all looking like a threshold function, right? But again, we don't care about the others. We care about, most of people are just using some simple solutions like this one, okay? Really, right? This works reasonably well until, let's say, you have some vanishing gradient on this, which is causing a lot of problems, like in the GAN model, then you use some liquid ReLU section, okay, or eLU. But we will assume the activation is always ReLU, okay? What is ReLU? ReLU is saying that if your output neuron in one layer is actually a positive number, right? And then your Y is also positive number for that after activation, okay? But what if the value is negative? If it's negative, then we just make it 0, okay? We will not have negative values. Okay? It's like on the negative side, it's zeroed out. Positive side, it's an identity map. Okay. So again, why this works? Just stacking those layers in this way it works. Okay, for now, just take it for granted, so that you can, it's also that not much deep theory. Okay. And so yeah, so here's an architecture. Right? So this is a one hidden layer structure. Okay, you can have two dense layers. Right, this is the input pixels, and then instead of directly go to 10 output scores, you have first get into a hidden layer, right, internal features. Okay, and then maybe another higher dimension, maybe 100 dimension, and then go from that high level features to that. Okay, you can even do more layers. Okay, this is called a one hidden layer neural network because there's only one hidden. Or we say the two layer neural network. Why two layers? Because we have two dense layers, right? Okay. Even though we have three tensors, but the input tensor is usually not continuous. Okay. One layer generates one output tensor. Okay. And here's three layer neural network because of three output tensors. Right. Or we can put two hidden layers, right? Because these green, these blue ones are hidden. Okay. This red is input, it's green output. Okay. Yeah. If cryptography, we can write it like this. And because of the, because of the template mapping, so we can do something like, we can take all these rows, right? So W2 for example, all those rows, right, for different images. And when we can average them out, and we can really see the average make some sense. Let's say here, this car, the average is, the average will be noisy, but you can see a car shape, right? And you can see a horse shape, okay? So the template thing really makes some sense, right? Okay, in order to train the model, so one thing is feature extraction, right? So after that, we do the prediction. So we say that Y hat is equal to Fx, okay? What's happening here? Equal to Fx, okay? But this is our prediction using this model if we already trained the theta, okay? But we also have a ground truth, right? And our training data will give this Y and give this X, right? But for a particular theta, let's say a random initialized theta, it will give another prediction, which is quite different from Y, okay? And we want to adjust this theta accordingly so that they get closer, right? So we need to have a measure of how far away they are, okay? So this is called a loss function, okay? And we use a loss function to train the model, back propagation, okay? So here's the example, right? So you have let's say you already have this input and then go to a boundary dense layer, and now these are the scores, okay? These are the scores again, right? And now, how do you connect to the ground truth to compute the loss? Okay, so here's what you do. Okay, so firstly, you will translate into a probability vector, right? Which means each one has a certain probability and they sum up to 1. Okay, for doing this, you are doing so-called softmax, right? You just take exponential of everything, right? Because exponential of everything, even the negative numbers, right, is always positive. Okay, but if you take exponential to the power of something, then if the exponent is very big, right? Your weight is much higher than the others. Okay, so here's example. We do this softmax function. Okay, and then e to the power of 3.2 becomes this value. But e to the power of negative something becomes smaller than 1. Okay, and you see this weight is really higher, right? Because this guy is 5, and after softmax, this kind of why we call it softmax, because after max this become a lot larger than this. Right? This is less than twice, but here it's many times, 8 times. Okay, and after that, this is a all larger than 1 values now, right? We don't have negative scores. Okay? But then we need to normalize them, right? To basically we divide all of them by their sum. Okay, then we will get a probability vector. So then what we do is, let me just go to one particular interpretation. Okay, and then we have the ground truth. The ground truth saying that, hey, this is 100% cap, right? This image is a cap. Okay, and the dog and maybe the kind of fraud should be 0%. Right? This is the ideal prediction. But here our probability vector is saying, hey, the cat probability is just 13%. Okay, and most likely I will predict the cat. Right? So there's some difference. So we will compare. Okay, a comparison function, one particular function to describe how two different probability distribution different is using the cross entropy. Okay, cross entropy, like defined. Right. And in our case, P is actually here, right? So you see the P is 1 times log of this value, right? And then you have a negative plus 0 times log of this, 0 times log of this. Because these are zeros, right? So really it's just a true class cap. It takes the log of the probability. Okay, so that's why previously we have just takes a log. So this is also called a sparse cross-entropy, because you know the real class, you just give the class and you get the value to the log. That's the loss. Okay, so this measures how far away your prediction, the score, is not good because this is a cat, but your score car is high. Right? And you transform to a probability vector and compare with the ground truth 1, which is 100% cap. Okay, and then you will get some distance, which is using cross entropy loss. Okay, now that you know these two have some difference, right? This is called one-hot encoding. Okay, now how do we say this is basically there are some distance, there's some error. So this we want to propagate the error back in each layer to tune their weight matrix W. Okay, how do we do that? So the solution is called a gradient descent. Okay, stochastic gradient descent. What does that mean? So basically, let's say you you want a y, right? But you got a y hat. Okay, right. So then there's a difference. Okay, then there's an error function of this. So this is actually a function, right? And because this y is another function of x. Okay, then this whole error function can take partial derivative of x. Okay, so we want to find a particular parameter w here to minimize the error here. So make this as close as possible. Right. So we start from a random w, like initializer, whether using Glorat initialization or random normal, it doesn't matter. Right? So it's like a starting from random location. Okay, but I will take gradient. Gradient go negative gradient direction. Which we will see, hey, which direction goes to the lower loss, the fastest. Okay, and then I go to this step, and then I take another step. Hey, this direction is even lower, right? And I go to, and then go to, and finally we will go to a location where the error is really small. Okay, really small, and that's basically the training step. What's the model fitting, the model training is doing. Okay, and we try to find this W that minimizes that. So you can see that it doesn't mean that once you reach the smallest point, whether it's enough for your application, that the error is small enough, that's another step. So the deep learning is really the best effort. optimization point. Okay. So this is affordable if we just have one dense layer, right? But we think about the deep learning models, right? In Google Net, we have many layers. Okay, so this kind of gradient, you compute gradient layer by layer, this will kill you. Okay, so that's why we need these TensorFlow, PyTorch to automatically help you do the gradient. You still need the gradient, but it's handled by the software. Okay, right. So this is another example that even if you can do AlexNet, right? You have neural Turing machine, right? Then this model is created, right? You don't want to do that yourself, right? Gradient. Okay, you want a software to compute it for you. I mean, the library. Okay. So let's take a look at an example of how this thing works. Okay, how different layers are propagating the error back. Okay, here example. Let's say you have the input, 3 input in your function. Okay, x, y, z. Okay, and then of this relation, right? X plus y equal to 3, 5 minus 2, right? And then times 6, 3 times minus 4 is minus 4. Okay, so this is a function. I think they don't work. Okay. Now what we want is, for example, we want to take a derivative. Let's say these actually are, in our case, these are the weight matrices. Right? So, okay, this is that. Okay, how do we compute? Right. So we want to take a partial derivative to x, partial to y, and partial to z. How do we do that? Right. So we know that we can write this as a q. Right. So we have 2 steps. One is this is q, and the second is qz, x plus y. Right? And then we can use the chain rule. So what is chain rule? Right? So if you have, let's say, y equal to f g x, right? So you can first take a derivative y over this, right? We write g as u. You can take derivative u, and then this u, which is gx, right? And then take derivatives. Okay, this kind of rule is chain rule. I hope you have an impression on this. This is the calculus. Okay, so different layers taking derivatives, just relying on this chain rule. Okay? For example, here, if you look at q, right, and because of this, q is equal to x plus 1, right? Take partial derivative x is 1. Okay, the partial y is 1 because the coefficient is 1. Okay, and if you look at f, take a partial derivative q is 1. It's z, right? Because the coefficient is z. It's a linear function, right? And then take partial derivative z is q. The coefficient is q. Okay, I hope you can see this. And after that, because we don't really need a q, right? This part is useful already, okay? But we need actually to x and y, but we know that q is a function of x1, okay? So what we need is we use chain rule, okay? We can using, based on this value, we can continue back propagate to x and y, okay? To the previous layer, okay? So here's an example. So again, so just the, so this f, so this can be ignored basically. F take a partial derivative of itself. Right? So this is 1, and 1 times anything. Right. Then if you take the chain rule f to z, right? Well, it's 3. Okay, because you know f to z is q. Right? Q is 3. Right. So q is 3q. And now we have f to q. Right? F to q. Right. F to q is z. Right. So it's negative. Okay. So this is the backpropagate value, right? And then you come to this layer, right? So to this layer, because now we have the -4 on this side, and we have what? Again, we have this layer. Right? Q take partial derivative y is what? It's 1. Okay. So that's why, you know, here we have this. Okay. So we have this thing is equal to what? This thing is -4. Okay. And this thing is 1, right? So this is 1. This thing. So -4 times 1 is -4. Okay, so this is the chain. Okay, right. And so we can also do similarly for x. Okay, so this is the same. Okay, because this is also 1. And so you know, let me see. Q to x, you know, Q to x is again -4, right? Because this is both are 1. Okay, so this is 1 and this is -4. Right? What can you try? Okay, so yeah, I see a question here. Okay. All right, so to put simply, let's say you have a f function in this layer. This is, okay, and you know, the parameter is xy, and the output z is from the next layer up to upstream layer, right? Or it should be downstream layer, actually, if you think of the forward, right? Is something that propagates back. Okay, so that is the output tensor, but input tensor to the next layer. Okay. This is kind of like, okay. Then what we can do is we can take this output tensor and continue to take partial derivative x and y, right? But we have, ultimately we have this L, right? So what I want to say is that we have multiple layers. Maybe this z is into another layer. Finally, this is loss. Okay, so it's like cross-entry loss distribution. Okay, and our ultimate goal is to take L to x and L to y. So because we want to find x, y, those weight matrices values to minimize L. Okay, but according to chain rule, we first go to this layer, right? So according to like back propagate all the way to z, we have this one. Okay, now we also know that for this f function, output z at input x and y, we have these two partial derivatives, right? Depending on the different f, we have different. Then what we can do is using chain rule, right? So we can say, hey, this L to x is really L to z, and then z to x. Right? This is chain. Similarly here. So what does this mean? This means that, of course, when you do forward propagation from the x, right, and using current weight, okay, you will get a z tensor, right? And that tensor will backpropagate into another gradient tensor, right? And this gradient tensor should also be in GPU. These two are all in GPU. These two also in GPU. Okay, and you know, there are a lot of values here, so that parallel process. Okay, and what you do is just for each layer you get the backpropagated gradient and the time with the current layer squared, right? So this, let's say, past the backpropagated layer is right now here, and then you know that for this f you have the gradient like this, right? You just can and continue backpropagate. Okay, so this is what the software is automatically handle this for you if you use TensorFlow and PyTorch. So you know, earlier people are using Cafe, right? So it's now also with Facebook, Cafe 2, and so I don't think it's clear enough to see, but basically what they do is they have this internally tell you how to create gradient, right? So you don't care about these things yourself, right? So they handle this. You only think about how to stack the layers and forward propagation, but it will try to backpropagate. And when backpropagate, it computes how those weights should be adjusted. Right? So weights are actually, you can see those weights as those edge weights. Okay, it's the same as a matrix multiplication. Okay, and I think it's a brief history we can ignore. Okay, so far what we see is you know, the Follick net layer, right? But as we said, we are just explaining what is Follick net layer earlier. Okay, but in reality, we never do a Follick net layer directly on the image, right? We always do a convolution on it. Right? So for different kind of input, you different kind of models. Okay, so the convolution net also CNN, right? Convolution neural network. So there are two names, CNN or CAPTCHAS. Okay, both are the same thing, right? Depending on how you like to measure. So the reason we want to do this is really, you know, we flatten this, there are too many parameters, okay? We don't want so many parameters like in the edge density, okay? We want to use less parameters, right? Otherwise it will not be computationally viable, right? But even though we specify the weights, the parameters to them initially, they should be meaningful, right? To be able to capture the you know, spatial locality in each image, okay? So let's take a look at why, you know, convolution net can reduce the number of parameters. You think about an image of this size, right? If you flatten, stretch it into this vector, right? And then we know that if you want to project this value to 10 dimensions, you need to time a weight matrix which is 10 times 3,000. This is crazy, right? 30,000. Okay. Now what we really don't want such a large weight matrix. We are now using some small filters, right? Just you know, this 25 times 3. 75 filter, right? And how we can still use a small filter, we can also generate another output tensor, right? So this is our goal, okay? So here, let's take a look. Okay, so now we don't need to flatten it, right? So because our convolution net really works with tensor. Okay, in the input image, because there's 32 pixels on each side, and then we have 3 channels. So the input pixel is actually tensor like this, right? And the first filter is doing something like sliding. Okay, what it does is it will slide over this face, right? So because it's image, right? There's spatial kind. Will slide this each face, and doing inner product with each stuff. Let's see. I think here we will explain this later. Okay. Okay. So let's assume the filter, the weights are fixed at 75 values, but it will slide here, here, here. Right now, it slides to this location. Okay. At this location, it will generate a neuron values at the output tensor. Okay. When you slide, you will get a bunch of these values, and then you get an output tensor. Right. So this is the idea, but the parameter is just 75 plus a bias value. But how do you compute this, right? So when you compute this, it's by inner product. Okay, so for example, this value here in the filter is timed with this value here in this patch, in this input image. Okay, and inner product may be not so clear, right? So let's just assume this x1, x3, x4. Okay, and then we have another. This is the input, right? This patch. Okay, and we have a filter. W2, W3. The inner product is just saying, hey, I will do x1 times W1 plus x2 times W2 plus x3 times W3 plus x4 times. Additionally, if you have channels, then the next layer you also do this, just sum them up. Okay, so it's like if you flatten them, these tensors, right, and then you are doing inner product. Okay. So yeah, after you slide, and then you will get an activation map. But this is the activation map, with one layer. Right? So this is just one here, because you do inner product along this 3 dimension. This 3 dimension is also in the inner product. Okay, so we just get one layer. Okay, but what you can do is you can do another. Right, you have a green, filter. This will give another activation, and you can do a bunch of them. Right? You have many filters. Right? And let's say you have 6 5x5 filters, small filters. Okay, and finally you will get an output tensor of 6 channels. Right? So you can see that how many filters you use, how many channels you get in the output tensor. Okay? And this output tensor becomes the output of the convolution. Okay, and here's a example here. Right? So you can do 5x5x3, and you get this. And you continue to do this. For example, now we can have another filter of 5x5, but as we said, each filter, right, is doing inner product. So the thickness should be the same. Right? So we have 6 layers that doing inner product. Okay, and the output will be something else. But if we do 10 such filters, then our output channel will be 10. Okay, and we can stack those again until the very end. Right, then we get a dense layer. Okay. And here is what we just described. And so, the idea is like, this layer is extracting some like lines. And here is extracting some high level features like the nose, the ear, the eye, and then the next layer potentially extracting some facial expressions. Okay, and then you can classify: is this person is happy? That person is angry? Or something. Okay, so this is a tutorial way of helping you understand. Okay, so now let's take a look at how the numbers play with each other. Right. So here you can see that we have, we have just a one kernel, this kernel, okay? And how we generate, if we slide to this location in the input tensor, how we generate this value, right? This by the way, this value is just one particular value in the tensor. When you slide, you get this, okay? So now, how can you understand their relationship? For example, why, we use 32, right? And then we slide a 5x5 filter. This gives you a tensor of size 28. Right? So we are making sense of how you can derive 28 from if you can compute. Okay. Any questions so far? So we only have 30 more minutes, so we probably will skip the break. Okay, so just to move forward. Right, so yeah, because we still have quite some slides. And so let's take an example, right? So let's first temporarily ignore this channel dimension. Okay, let's just look at the phase dimension of this space. Okay, and this is something that is sliding. Okay, this is a filter, right? And this is the input tensor phase. Okay, right. So this 7 here is equal to 32 dB. Right? This 7 by 7, but we are do a filter of 3 by 3. Okay, that's 5 by. And then let's see how we can calculate that relationship. Okay, get some intuition. If you do this, and then this is stride 1, you move 1 at a time, right? So what you will do is you will have 5 of them, right? So you think about it. This first one, the second one, the third one, the fourth one, the 5. So you will get 5. Okay. So how do you get the? So by the way, this vertically is the same. Right? After this, we will do the next one, which is something like this. And so you will then move to this one, and this one, and this one. But after this row, you will do this one, and maybe this one. Okay. So this is the idea. So the vertically it's also 5. Okay. How can you compute this 5? Right. So this is actually because you think about it, right? So the center, let's say you are centered here, and your center moves to here. There's only 5 values. Right? There's because the filter is 3 by 3. Right? So the center is here, and you will cut out the margin 1 by 1 each side. Okay. So it becomes smaller from 7 by 7 to 5 by 5. Right? In the previous example, it's become 32, become 28. Okay. And we will see how we can solve this problem later. Okay. So far, each step we just move, stride 1. Okay. We can also do stride 2. Right? These are happy families. What does stride 2 mean? Each time we move 2 pixels inside. Right? If that's the case, we can only fit 3 by 3 out. Vertically, it's the same. Okay. So if you increase the stride, actually the sampling rate is even lower. Okay. And how about stride 3? Right. If we remove 3 columns at a time, then we actually there's no overlap. We move to another, let's say. So the next one will be this. But the third one will be, we don't have anything, right? So it cannot work out this way because we don't have anything to time for the third slide. Okay. So it doesn't fit. Okay. So let's see the numerical relationship, right? So how do we get 5? Because so with the 3 and this is 7, right? 7 minus 3, but we do plus 1 back, right? So this is similar to how we compute. For example, you have 10 values, 1, 2, all the way to 10, right? And how do you compute how many elements are there? Right? It's 10, the last element minus the first element. But you do plus 1 because there are 10 elements, not 9 elements, right? Similarly, if you start from 2, 3 to 10, right? So how many elements? 9 elements because you don't have 1. Right? How do you compute it? 10 minus 2. But that's 8. You still need to plus 1 back. Okay? So that's why we have this. All right. So, but again, because each time if you move 2, then you should shrink by twice. Right? So it's by 2 by 3 because 3 is really not a the other fraction element. Okay, not an integer. In that case, you cannot do that. You have to make sure it's integer. But another thing you can see that we always have, the filter size is always 3, 5, 7. That's those kind of odd numbers, not even numbers. This is because we want to have some center in here. Like we want to have some center, and then somewhere here are symmetric. So otherwise, if we have 4, then there's no center. The center is here. Right? It's not a particular pixel. Okay. And so as we said, there's a problem so far, right? Each time you do a filter, the output tensor will shrink, right? Because the center slide only through the white area, right? So the output tensor will shrink by 2, okay, 1 on each side, right? So how to compensate for that, right? The easy way to do that is, hey, let's say this is your input tensor, right? But if you slide, let's say you slide the tensor starting from the first location starting from here, you will shrink, right? So our solution is say, hey, you don't start from here. You also start from the first pixel here, right? So as a center, you use this one. But then there's a problem, right? So because in the data, you don't have these things, okay? So an easy way to compensate this is just pass the boundary all with zeros, okay? If you pass the boundary with zeros, then your output size will be the same as the input size, okay? So this is actually, I think it's the default setting. Let's see. Let's take a look at, let's say, look, count to D. Okay. So this is like a, you can start to stride, but this is width stride, height stride can be different, okay? And the padding, okay? So padding is valid, right? So, and you can say it's the same. Same is you pad it so that the output tensor size is the same as input tensor size. It will do all the calculation for you yourself. So you really, this is conceptual understanding, but why you need to use a library? Because you don't care about the details, okay? And gradient, all this stuff. Okay, here now the input is 7 by 7, right? The output is still 7 by 7, okay? Because you can slide the center through each pixel, okay? But the boundary, you don't have any values there, you just pad with 0, okay? And for 3, of course, you pad with 1, 0 pad with 1, but because, 3, each side you have 1 pixel from the center, okay? And if it's 5, then you need to pass 2, which means, you need a 2 rounds of 0, but you have another round of 0 also, okay? So when you have a 5 by 5, 5 by 5, is this number right? I think it's good. Let me try to make it 55, yeah, okay. So you still have a center there, right? So the center is, oh no, so I think it's even 1. No, okay. So this is 1, okay, this is 2, this is 3, this is 4, this is 5. Okay, then it's okay. And our center is here, okay? Because this is 0, these values are padded with 0, okay? So on each side, you actually have 2, size 2, okay? So that you paddle with 2. If you have 7, then each side you paddle with 3, because 3 plus center 1 plus 3 on the other side, okay? But once you use libraries, they will do this for you. They will calculate this. Okay. And so in this way, if you want to not shrink, right, because then you can use same for that, right? And we'll adjust the 0 padding, make sure it doesn't shrink. Okay, because if you shrink, then you cannot do deep learning, right? You shrink to 0, shrink to 1 quickly. And so here's the example, right? We'll do some calculation. So assume that input volume is 32 by 32 by 3, and we have 10 filters, right, with stride 1 and pad 2. So what will be the result? What will be the output tensor value? I mean the size, the shape of the output tensor. It should be another 3, 3 values, right? It's a tensor. Okay. Who can tell me what can be the answer? According to what you just learned here.
The same size.
Yeah. Yeah, please go ahead. Good thing, right? Please go ahead.
I was saying it'd be the same size. 10, 5, stride of 1, and a pad of 2 are the result of the formula from the previous page. Essentially, you're just passing a center value for every pixel in the original data set and getting the same size result set.
Yeah, correct. So basically 32 is still 32, okay? The only difference is that, we have 10 filters, right? 5 by 5, because we had 2, but according to here, we describe. If you have 5 but 0 padding with 2, then it's the same size. It's still 32. But we have 5 filters, right? We have 10 filters. If we have 10 filters, the output is 32 by 32 by 10, okay? I hope you can see that. According to our previous formula, you can also see that. Okay, so keep in mind the inner product is on the channels, right? So with each filter, output is just 1 number, but we have 10 of those, so the channel is 10. Okay, And so how many parameters are there in the layer? Right, so this is another question. Who can answer that? So here again, let me clarify. Okay, so right, so you know, machine learning model is X and W, right? So and we go to Y. Previously, we were talking about what's the shape of Y. Now we're talking about the shape of W. Okay, this is X, right? But of course, F here is not density; it's convolutional. So the filter weights are much smaller. The size is much smaller. But who want to have a try? Okay, so let's give you an answer. So it's very small. Okay, just want to show it's really small. Okay, because we have 10 filters. Each filter has 76, and 10 is just 760. Okay, but why each 5x5 filter itself contains 76 parameters? This is because you think about this filter here. Okay, this 5x5 is 25, right? And but you know, when we do inner product, we also need to do inner product with input on the channel layer. Right? So that's 3 here. Okay, but then we have a bias term. Okay, you remember we have a bias Wx plus b. Okay, this b is, you know, we need also this b. Okay, for each filter we need 1. Okay, and because you think about this inner product, right? W1, X1, W2, X2, W3, X3 for this filter, plus B. Okay, and then we have another kernel, we have a B2, B3. Okay, so each filter will have a bias. Inner product plus a bias. Yeah, here's a summarization of the formula, but I think you can read it offline. Okay, maybe in deep learning course they will cover more, but all these are automatic. And here are some common settings, as I said. So, you know, the filter will always be, you know, 3x3, 5x5, 7x7, and that could be 1 by 1. Okay, so what does 1 by 1 mean? 1 by 1 means it's you know, it's basically kind of, you know, you don't scale things, right? So you are only doing inner product along the channel. Okay, so if you have a tensor, which is 1 by 1, right? So it's 1 by 1. Okay, then you are just doing along this channel layer. Right? So if this is 3, then it's just a x1, x2, x3 with a w1, w2, w3 inner product. Okay, so you are not changing anything else. It's kind of like averaging on the channel. Right? So doing a weighted. It's like doing a density on the channel for each pixel. Okay. Right. So yeah, let's go a little faster. So this is the summary of the convolution network so far. We have covered the fully connected layer, right? And we have covered the convolution layer, and we'll also mention briefly what is the ReLU, right? Why we need it, right? Because otherwise you stack a bunch of near-linear layers together, it's still a linear layer. Okay, then it cannot capture complicated things. Okay, but why nonlinearity helps? That's something that you just take. Okay, so because, you know, it's super complicated and still there's a lot of research there, okay, right, regarding optimization. Okay. And another thing we talked about is in early models we need the pooling. Right? So actually we don't need pooling in later models because convolution can do the pooling kind of task. Right? We can shrink it. Okay, and early models they do the pooling. So let's take a look at what the pooling. Right, the pooling is really trying to make the face size smaller because we gradually will increase the channel. Right? Finally, we want a bunch of independent features. Okay, and so we will make the face size smaller. Right, so every few layers we will reduce the downscale of the image a little bit. Okay, for example, this image is too big. We want to downscale to half of the size on each side. Right, so the area will be 1/4. Okay, that will lead to a lot smaller, you know, RAM, you know, memory space required in GPU to process this. Okay. And how do we do this? Right. So here you can see that, for example, we want to downsample. Is there any way that we can make a meaningful downsample? Right. So, for example, here, if you look at this downsample, it's like every every 4 pixels is made into 1 pixel. On each side, every 2 pixels condense into 1 pixel. Okay, and so it's like a patch of 4 pixels becomes a new pixel in the output. So how can we do that? Here we are doing different methods, right? So one method that's very popular is called max pooling. Okay? So what is max pooling? Let's say for this patch, we just take the max value 6. For this patch, we take the max value 8. For this patch, the max value 3. Okay. So this logically, you can also think of this meaningful. Like, for example, if you downscale some of the photo, right? So if you have some, maybe originally here you have some background and you have a very bright, let's say the red color. Right? After the downscale, you should keep the red color instead of the background. Okay, so that makes a lot of sense, and this also makes sense if you think from the biological point of view, right? So from the neuron, real neural network point of view. Right? So it's if you fire some signal, the signal should be highlighted. Others that are not so strong should not. Okay, so that's some way to justify max pooling, but you can also do something like average pooling. Right? So just take average value. Okay, that's awesome. But we will assume you just do max pooling. So max pooling, there's also a formula to compute the size. Right? So because you can decide the pooling. Right? So here we are doing a 2x2 filter with stride 2. So if you have a 2x2 filter and you also do a stride 2, which means each time you stride 2, right? So then the output will be this size. Okay, so there's also a formula to compute this, but by default, stride max pooling, we always do not overlap these things, right? So when we do convolution, we probably will have something that overlaps it. Right? So we will have stride 1. Right? So max pooling, we usually don't do that. Okay, we always make sure they don't overlap. All right, so that's pretty much for neural networks. Okay, so and again, so here's a bunch of systems that you need to be aware of. So Caffe from Berkeley, originally derived now by Facebook. Because Caffe is in C, C++ is very fast. Okay, TensorFlow is just super, but originally TensorFlow 1.0 is not easy to use. But we will go with TensorFlow 1.0 because it's developed. Maybe the project developed 1 or 2 years earlier. It's a lot of workload to change back. And TensorFlow 1.0 is very low level. This also helps you to get deep understanding. And then you need to understand a little bit TensorFlow 2.0. It will be easier. But if you go deeper layers and then you come back, it's going to be easier. Okay, and this is original from Montreal and now by Google. Okay, original all these are from the academia, right? So then Facebook too, but PyTorch really they try to combine them together. Right? So because PyTorch is really Python, they want some backend Caffe too to make it fast. Okay, and there's a lot of other things like MXNet is like an open source version, the Apache version. Okay, but I would recommend don't use these things. Okay. These are the early games where people try to compete and be the major dominating library. But right now, just stick to either PyTorch or TensorFlow. Okay, and TensorFlow you should start from 2.0, and then learn a little bit of 1.0, but they will be outdated. Okay, because it's not so user friendly. The reason because the latest models are all implemented using Z2 libraries. Okay, and if you use the other models, maybe it's a couple of years earlier. You see how people writing papers. Right? You see the citations. Okay. So now these two are clear winners. Right? Just to be safe, just choose one of them. Just to begin with. For example, I choose TensorFlow. Right? Okay. So so let me see how many pages we have. Okay. So TensorFlow itself is very low level. So usually we will use another API on top of TensorFlow called Keras. We have a sequential model, and like our previous model, we can do something like this, right? We can add a convolution layer, and batch normalization is what we don't cover. But usually, if you see the training is not doing well, you can add a batch normalization before your activation. That will help things, okay? And then activation after reload, you do the max pooling. Right? This is what we talked about earlier, and you can do a dropout after that. So these are things that help you improve, and we are not covering them, okay? And then you can do convolution, activation, and max pooling again. And convolution, activation, and max pooling. Okay, and finally, you do need to add a density. You can add a bunch of density, right? So that gets you the model that we described earlier, right? So you can see that Keras is really and then you can train. Right? You compile a model using Adam. So optimizer is the gradient descent we talked about. Right? Go to the valley for the loss function, and it's all very simple. Just assume which optimizer you want to use, and then what's the loss function? We talked about it's a cross entropy loss, right? And then the portable metric will for accuracy. Right? Among 100 images, how many images are correct? Basically, intuitively, that's the meaning. Though your batch may contain more than 100 images, okay, or different. Right? And then you can have different batch size because GPU has limited run size. You cannot get the entire data set. Right? If you have 1 million images, you are doing 128 images a time. Take the gradient and then take the average. Okay, and because when you take the average, the gradient direction will be approximately close to if you take the entire data set. Right? So the variance is already very small. Okay, so this is called a stochastic gradient descent. A variant of that is called average. But all these things you can just take them. Okay, and then you train epochs. Right? And this is like how many steps. Yeah. Right. But here, epochs means how many batch sizes. Right. Until you kind of like scanning the whole data set once. Okay, that's one epoch. It's like you scan the whole training data set 250 times. Okay. So this is basically something that you need to understand. And these things will appear in our demo code for you. And again, you don't need to change this code. This is for you. Right? So you just need to use this code and get deep understanding of it. And then we have some other models. How you put this deep learning model into the whole big pipeline. Right. So the big pipeline is for you to break a WordPress plugin. Okay, WordPress is a website. If you want to make a website, you can use WordPress. It's much easier than doing from scratch. Okay, and for different things you want to show on the page, you can use different plugins. Right. For example, if you want to add a captcha to verify that the user is a legitimate user, it's not a bot. Right. So then you can install this plugin and then put this plugin module somewhere, and then when people log in, they need to do a captcha. Okay. So this WordPress plugin actually, they will generate these images. Okay. And what our project is doing is firstly, remember we are just doing the image classification, right? We are not doing complicated like segmentation, or we are not segmenting these networks out. So what we will do, we will still use a traditional computer vision stuff, right? So we kind of compute the connected components, right, of these stuff, like computer contour. So we'll get 4 different models of black pixels, okay? And for each black pixel, we'll dig it out, okay? And throw to our classifier, right? So we first using computer vision, like OpenCV library, we will dig out these 4 components, right? So basically 4 connected components of black pixels in some sense, if you look at it, okay? But when you work on the project, you'll see more details. It's not so simple, okay? And then you get this, each component, you include a little bit of boundaries, you get an image for a letter or a digit, right? And then you go through the deep convolution network we give you, right? Just like what we described earlier. And you expect the output to be 2, right? If it's 3 or 5, then something's wrong, then you need to fix it, okay? So I mean, you don't need to fix that. The model will fix that by backpropagation, okay? And here, we're using OpenCV library, right? So OpenCV library is a computer vision library for conventional stuff, okay? Now they also have deep learning models, but originally, before deep learning, OpenCV has been there for a long time. Let's say if you don't use a convolution app to extract image features, there are some like I think hog feature, etc. In OpenCV, they have a lot of ways to work with images. Okay, it's like a coding version of Photoshop. Okay, and you can dig out these connected black pixels, right? Then you will get 4 components. Okay, and then you dig them out into different images, say to a training data. Let's say each you will actually have 1 folder of letters for each letter, okay, letter or digit that you want to classify. Okay, and then the output. So here's the solution. Right? Once you dig out, you train the model. After you train the model, next time we give you a new image, test image, right? So you will take each pixel as one, right? And then what you do is you throw each of the component into the trained model, and it should give you the label. Okay, And so this is basically right. So we will release a project tonight, and you will have, I think we will put it to 1.5 weeks, okay, to finish. Right, so. All right, so, and because as we said, this thing is so easy to break, right? So there's no value here these days to really ask people to input those levels, right? So there's still some website maybe use this, but it's really not so meaningful. If I want to attack you and I know some of the deep learning, I can easily do stuff, right? Okay. So what happens these days is that Google actually use a recapture v3 version 3, right? Previous version maybe ask you to input something, right? Now they just give it up, okay? They just say, ask you to tick, I'm not a robot, okay? And if you tick, then you pass, right? So of course you can let a you use the bot to tick, right? Because you can zoom in a particular box and then tick. Okay? But bot's purpose is to repeatedly register for account, etc. Right? So then you will be able to analyze things. Okay, so let me see. So here's the introduction of Google's CAPTCHA, right? So basically, you will see this bot can tick again and again from the same IP address, and then Google will have an algorithm to recognize it's a bot. Okay, the first time it will always pass, unfortunately. Okay, so this is solutions. I will leave you guys to read this. Okay, so basically, early on, like people use image challenge. So then there's also audio challenge. You read out something and then you input text. And finally, there's even the game chat. Ask people to play some games, quick games. Okay, this also is no longer useful because we now have the game player, right? So we just show you earlier on the page. It's a deep reinforcement learning. Okay, so basically, Google solution just give up. It just ask you to do, right? So this is what happens these days. So you can see that deep learning is revolutionized. Oh, this is the last time I think you can ignore this page. If you have interest, you can read some of the articles, but like how to do TensorFlow to recognize numbers on doors or on cards. Okay. Yeah, I think that's pretty much it. And you can take a look at Google Recapture and watch some video introduction of it yourself. Okay, so if you are interested. Okay. I think that's the last of this stuff. And before I end this class, and tonight I will release this. I will release this assignment. Okay, before I let you go, I will take some attendance. Okay, starting from this week, we need to take attendance. But I won't take everyone. Okay? I just randomly sample 10, and if you are here, just let me know. Okay, Joshua, are you here?
Yeah.
Okay, let me sample. Mohammed Junaid, are you here?
Present.
Okay.
Present.
Okay, thank you. Shana, are you here?
Yep.
Okay, thank you. Chun Yao Chen, are you here?
I'm here.
Okay. Praveen, right? Praveen, are you here?
Yes, sir, I'm here.
Okay, thank you. Daniel, are you here?
Here.
Okay, thank you. And Varun, are you here?
Yes, I'm here.
Okay, thank you. Philip, are you here?
I'm here.
Okay, thank you. And I think we sample one more. Two more. Santosh, right? So sorry, Santosh, are you
Yes,
here?
sir. I'm present.
Next time I may sample from the bottom. Okay. Let me. Piyush, right? Am I pronouncing this correctly? Piyush?
Yes, sir. Piyush. Yes, sir.
Piyush.
I'm present.
Okay, thank you. And we have another list which only have one student because of pandemic. So, Kamal. Kamal, are you here?
Yes, sir, I'm here.
Okay, thank you. All right, so that's end for this class. And yeah, I will see you next week. If you have any questions, feel free to ask me. I will be here for maybe 1 minute. And I don't hear any question, I will stop. Thank you.
I didn't hear my name at roll call.
What? Your name, right?
I didn't.
So yeah, basically what I did is I take everyone present and then I sample someone. If I sample someone who is not present, I will cross it. Otherwise, I will by default assume you are here. It's okay?
Sure.
Yeah, because we have.
Okay, yeah, I see it. Okay.
So we cannot spend half a class.
Just want to make sure.
Okay. All right. Any questions? If you want to ask it, it's time to ask me. Yeah, I see a chat box. CN consider more for image. Yeah, CN is really for images. Okay. Yeah, have a good night. Okay. So CN is for images, and there's also graph convolution for like a social network, this kind of graph data. And there's also transformer, right? So, or recurrent neural net for sequence data, and especially for natural language. Okay. They are the major categories. So, and there are also advanced stuff, right? So different kind of loss function, like triple loss, etc. And you also have other architectures like generative adversarial networks and a bunch of others, like reinforced learning, different schemes. So there's a lot of things to study if you want. Right? So there's also neural architecture search, because how you design these layers. Right? So there's a net, this kind of stuff. Okay. But again, so you don't need to understand all these things as long as you understand what you teach, at least after the break. That's good enough. Thank you. I think I don't see a new question, then I will disconnect. And this video will be uploaded to YouTube. I will send an announcement with this link. Okay. Then see you guys next week.